So hello everyone. In this video, we are going to discuss about the naive-Bayes na classifier, which is the lecture 5 of our course, ComSci 197. So this will be the outline of the presentation. So first, we'll have a quick review on probabilities. Then we'll discuss briefly the Bayes rule or the Bayes theorem. And lastly, we will discuss the assumptions in the naive-Bayes classifier, how to train it, how to estimate the parameters, and lastly, we'll show you how these concepts may be applied in a certain application, particularly for spam filtering. So these are the references for this presentation. So I've used some data from Agbaneje's presentation from EuroPython 2018, although I have modified the most of the computations. And then most of the solutions or most information about naive-Bayes, as well as how to apply it in spam filtering, was taken from Jurafsky and Martin's article. And lastly, about the review for probabilities from a probabilistic perspective by Kevin Murphy. So let's have a quick dive on the review for probabilities. So first is what will be the probability of the union of events. So suppose we have two events occurring, A and B. So the probability that A occurs will be P of A, and the probability that B occurs will be P of B. Okay, and then there is also a possibility that A and B will be occurring at the same time. So we can denote that, or we can see it here in this Venn diagram, which is denoted by P of A and B, or may also be read as P joint probability of A and B, or the intersection in the set theory na notation, the intersection between A and B. Okay, so in order for us to take the union of events, so we can denote it using probability of A or B. So in other words, in the set theory notation, that will be taking the probability of A or the probability of B or the probability of both A and B. Okay, so we simply take the sum of P of A and P of B minus the joint probability of A and B. So this joint probability refers to this part wherein A and B are occurring at the same time. Okay, so since this intersection is already part of P of A and the P of B, so we make sure to subtract that in order to make sure that the counting is correct and it's not including the duplicates, right? So what if the two events are mutually exclusive? So the sets are disjoint, as you can see, which means that the intersection or the joint probability between the two events are 0. So to take the union of events, we simply take the sum of their probabilities. Now, let's move on to the conditional probabilities. So it is denoted by this bar. So we have the probability, what will be the probability of A given the occurrence of B. Okay, so that will be the joint probability of A and B divided by the probability of B. Okay, so if we see in this Venn diagram, so what we actually look for is this part, the intersection. Okay, so this is the part where both A and B are occurring. So what will be the probability of A given this whole probability of B, given that this B has occurred? So we essentially take the fraction or the probability or the joint probability of A and B divided by the marginal probability of B. Okay, and we could actually define similarly for probability of B given A. So essentially it will be the concept will be similar. That will be probability of A and B divided by the probability of A. Okay. So now let's just have a quick walkthrough. We have this probability of A, and then the probability of B. And the probability of B given A will be the joint probability of A and B divided by the probability of A. And the probability of A given B will be the probability of A given divided by the probability of B. And using the product rule or using simple algebra, we can actually compute for this joint na probability from this equation itself. So we have the probability of A and B equals to the probability of B given A times the probability of A. And from this equation also, we can compute for the joint probability of A and B. That will be equal to probability of A given B times the probability of B. And this is actually the product rule. So now at this point, what if we are interested with the probability of B given A? Okay, so but since this is unknown, and actually we can compute that from this equation, which is in which the joint probability is equal to the probability of A given B times the probability of B, which is computed from this equation. So similarly, if we are interested with probability of A given B, we can compute for the joint probability from this equation also, right? So as you have already seen in the or already mentioned in the previous slides, we have the joint probabilities, and this refers to the likelihood of different events occurring at the same time. So in this Venn diagram, so the joint probability would be this intersection between the probabilities of two events. Okay, and from the previous slide, we have already shown that this joint probability may be computed from this equation, right? So probability of A given B times the probability of B. So given a joint distribution of two events, A and B, we define this marginal distribution as follows, where we are summing up overall possible states of B. So combining the definition of conditional probability with the product and sum rules yields the Bayes rule, or called the Bayes-Smith theorem. So you already know that this conditional probability is essentially equal to the joint probability of A and B divided by the probability of B, wherein this joint probability is essentially equal to this product of P of A given B and P of B, right? So we have this final equation for the Bayes rule. So the probability of A given B, that is the posterior, and it may be computed from the likelihood or the probability of B as true given A as true, likelihood times the prior or the probability of A as true. So this is the knowledge. So we already know this. This P of A may be easily computed from the data that we have. Well, the marginalization is the probability of B as true. Okay, so now let's have an example. So before that, let's discuss about this bag of words na classification. So because what we want to do is to classify emails as spam or ham.